Hi everyone, welcome to another video on using Excel. In a previous video, we had looked at one of the methods of checking if a data set is a normal distribution. The method we used was the Harke-Bera test, which is one of the simplest ones that you can perform using Excel. However, it's not the only one. Another very common method is the chi-square goodness of fit test that we'll explore in another video. A quick word on normal distributions. Remember that a normal distribution accurately describes many naturally occurring phenomena that we usually come across. It is a very well understood distribution, and it has a lot of applications with different statistical tools. And once you have identified that a distribution is normal, all of the precepts of a normal distribution would be applicable to that specific distribution in question. Having said that, let's look at the normal distribution a bit more before we start looking at how to use Excel. So within a normal distribution, what you'll generally find is that it's a bell-shaped curve or a bell-shaped distribution, also known as the Gaussian distribution. It is symmetrical around the vertical axis, as you'll find that the distribution of data is equal on both sides of the vertical axis. It is completely described by two numbers. So any normal distribution that you come across, you can describe it by just the average or the mean, also sometimes known as the expectation of the distribution, and the standard deviation of the distribution. An important concept in relation to a normal distribution is generally known as the 68-95-99 rule, sometimes also known as the 68-95-99.7 rule. Now, what does this rule mean? What this rule means is that for any given normal distribution, generally 68% of the data points of that distribution lie between +1 standard deviations to -1 standard deviation, which is this area that you're looking at between these two vertical lines. That's supposed to contain 68% of the data set. An extension of that would be 95% of the data set lies between +2 standard deviations and -2 standard deviations, and 99.7% of the data set lies between +3 and -3 standard deviation. An important caveat here is that while you look at the plotted normal distribution on the graph here, and it seems like that the graph touches, or the distribution curve touches the x-axis at the +3 and the -3 standard deviations. However, that is not the case. That's just a visual aberration. In reality, the normal distribution stretches till infinity and then eventually becomes an asymptote, which is a curve that continues till infinity. It appears to be touching it, but it doesn't really touch it. However, for our discussion, remember that majority, or 99.7% of the data, lies between +3 and -3 standard deviations. And that is a very helpful property that we'll look at shortly. A quick word on the formulation of the standard deviation. You will see formulation of the normal distribution. You will see that the formula that you have on the right hand side is a fairly complex formula. However, two key characteristics to note here is that apart from the value of x, it just uses two additional points, which is the mean, as represented here by mu, and the sigma value, which is a representative of the standard deviation of that distribution. So given these two numbers, the mean and the standard distribution, you will be able to describe any known normal distribution. So how do we use some of this information to plot a normal distribution within Excel? So let's quickly jump onto that. So we'll begin with an actual question and then try and utilize some of the information that we just saw and see how that can be used to plot the normal distribution within Excel. So scenario 1, we have 100 students at a university who took an exam, and the mean score was 60 marks. In this case, the assumption is that the total marks are 100 marks, though it's not written. So the mean score of the team was 60 marks and the standard deviation was 10 marks. Assuming that the marks were a normal distribution, generate the data set. So how would we go about with this? Remember that using the previous rule that we just saw, which was the 68-95 99.7 rule that we just looked at, almost 100% of your data set is going to lie between the +3 and the -3 standard deviations. So that will become our important point in order to plot this distribution. So let's begin. So let's say that the minimum score that we can get on this, so the minimum score that we can get on this is going to be the mean minus 3 standard deviations. So what would be that score? So let's say the mean is 60 and the lowest point that you can get is going to be -3 standard deviations. So 60 minus 3 into 10, that would in effect be the lowest score of the distribution. And then this distribution will keep on going all the way till mean +3 standard deviations. So how do we do that? Let's say we just plot out the points between the lowest to the highest. So we're just going to drag this till we reach 90. Remember, 90 is going to be nothing but the maximum score of the distribution. So let's see where we are with this. Okay, so let's just remove the extra points here, and that leaves us with the data set all the way from the lowest, which is 30. As you can see, 30 is nothing but the mean -3 standard deviations all the way till 90. Remember, 90 here is nothing but the mean +3 standard deviations. So this is our operative data set, and let's begin with this. So given this data set within Excel, we have a very helpful formula. This helpful formula gives us the probability that we can expect for any given value of that data set, the probability of occurrence of that value within the data set. So within Excel, that is given by the formula norm.distribution. And as you can see, the description, it says returns the normal distribution for a specified mean and standard deviation. So how does this formula work? So first of all, what is the x? The x is going to be the numbers that we have plotted all the way from the minimum value of 30 all the way till the maximum value of 90. The mean of this distribution is nothing but 60. The standard deviation we have just looked at is 10. And for the cumulative, remember there are two options. The option true is for a cumulative distribution function, and the option false is for a probability mass distribution function. So what we are going to look as the probability distribution function. So the option that we'll choose is false because we are not after cumulative values of the distribution. So let's choose false. And that is the probability. So what this means is that the probability of getting a score of 30 when the entire team's scores lie between 30 to 90 is this number, which is a fairly low probability, but that's the probability. So let's go ahead and populate the probability for all of these. There we are. As you can see, if you explore the data set that we just generated here, the probability numbers, you'll see that as the score increases, the probability of that score will also increase, and eventually the highest probability happens around the midpoint, which is probability of almost 0.04. If you see 0.039 or 0.04 almost. So the highest probability happens at the center or at the mean of the distribution. This is something we anyways come to expect from the concept of how a normal distribution bell curve shape looks like. So let's plot it on Excel. So in order to plot it, it's a very simple method. If you just select the data distribution, you go to insert, go to recommended charts, and it automatically shall give you the chart. And let's use this one right here. All right, so that's how our distribution is going to look like graphically. Let's bring it up. Okay. All right, just needs a bit of adjusting, and here we are. So that's how our distribution is going to look like or appear on this one. Okay. So now, very important thing, remember that the highest probability that we saw appeared at the central point. So if the central point is 60, which is right here, as you can see, this is the point where the bulk of not the bulk, but the highest probability value occurs at 60, almost close to 0.04. Okay, so we've just seen how you can generate a normal distribution given just two numbers. We had the mean and we had the standard deviation. So now let's go ahead and extend this idea and take this example to another case right here, which is given out here. So similar case, we have another distribution in which we had students who had participated in a university exam and their mean score was 70 and the standard deviation was 5 marks. So again, let's begin the same way. Our lowest point here is nothing going to be but the mean minus 3 times the standard deviation. The standard deviation here is 5. So that's in effect going to be our lowest score of the distribution. And now what's going to be our highest score? Remember, our highest score is going to be nothing but the mean, which is 70, and 3 times the standard deviation, which is 5. So our maximum score is going to be 85. So let's plot this out first. Okay, and let's just stretch this out all the way to 85. Okay, let's take away the extra points here. And there we are. We have the required set of numbers here. And now using the norm distribution function, we can simply plot the probability for all of these points. So let's do that. So if you go to probability and using the same norm distribution, remember the x value is this. The mean in this case that we use, just to remind ourselves, the mean is 70 and the standard deviation is 5. And since we are interested in a probability distribution function, not a cumulative distribution function, we use the option for false. And there we are. It has generated a probability number for us for 55. Let's go ahead and we've gotten all the probability numbers here. Okay, now let's go ahead and plot this out. So again, if you go to the option for insert, you choose the recommended charts and use the same option here, and that will generate a graph for us. Let's go ahead and move the graph here. All right, so we have another probability distribution graph here. Again, remember that the probability is highest at the central point, which is at the mean. That number is 70. So you can see the maximum probability occurs at the center. And just marked it out for easier visibility. So this is how you can generate a normal distribution given those two numbers, the mean and the standard deviation. So given this normal distribution, a natural question that you will always encounter is how similar or how different are these two normal distribution curves? What is the central point like and what is the spread? Are these two curves similar? Are they different? And if they're different, how are they different? So remember that you can always have a normal distribution curve which is more squeezed or more flattened than the other one. But by just looking at these two diagrams right now that you have on the screen, are you able to easily figure out which one of these is a narrower distribution or which one is a flatter distribution? Probably not. And that is where a concept known as a standard normal distribution is very useful. So what is a standard normal distribution? A standard normal distribution is nothing but one which has a mean of 0. It always has a mean of 0. And then instead of the x values that you see right now, for instance, on the data set, you have the x as 55, 56, 57, and so on. It always uses a more standardized value or a more standardized concept known as a z-score. So all of these values that you see here, 55, 56, 57, so on, will be replaced by their corresponding z-scores. What is a z-score? A z-score is basically a number which tells us how far a certain value of x is from the mean as measured by the number of standard distributions. Again, that's quite a few words, and let's see how would that play out within Excel. So to understand that, the first thing that we'll do is let's go ahead and copy this data set, and let's generate the normal standard distribution. To generate that, we just copy it here. And now let's generate the z-score first. So the z-score will be generated by this formula. So basically what we'll do is we are going to reduce all of these numbers that you see right now over here into their corresponding z-scores. How do we do that? The way we do that is for each of these numbers that you see out here, we are going to see how far is it away from the mean. So what was our mean for this distribution? Our mean for this distribution was 60 and the standard deviation was 10. So how far is it from the mean of 60, and then divided by the standard deviation, so that it tells us how far is the number 30 from the mean 60 when stated in terms of standard deviation. All right, so it gives us -3. So in other words, what this is telling us is that the number 30 is 3 standard deviations away from the mean score of 60. That's what -3 means here. Now let's stretch and extend this formula right till the bottom. Okay. Any guesses on what we'll get for 90? 90 is the farthest point, and there you are. As you can see, the number 90 is actually +3 standard deviations away from the mean score of 60. So now that we have understood how to generate the z-scores that we have here, we have to go ahead and use this in order to create a standard normal distribution. So previously what we just plotted above was the normal distribution in Excel. Now we're going to plot the standard normal distribution instead of the normal distribution. So let's make that happen. Let's just write the probability out here. And again, we're going to use the norm distribution function. In case of the norm distribution function that we have here, again, remember the values that we will certainly utilize in this in terms of the x, the mean, the standard deviation, and the cumulative. So what is the mean that we have here? So the mean value, as you can observe, that we have here is nothing but, remember the mean was 60. So let's say this is my mean. Okay, and then what is our standard deviation? Remember our standard deviation was 10, and which again, in case of a standardized normal distribution, the standard deviation we can use will be 1, because remember, all of your distances are measured in terms of standard deviations on this scale. And then so we begin with this. So we have the first value on this, which is going to be the z-score. Instead of the x, we have the z-score now. The mean that we have, the mean for every standard normal distribution is 0. The standard deviation is 1. And are we going to use true or false? We will use false because we are after the probability mass function, not the cumulative in this case. If we do that, this is the number that we've just generated. And let's drag it down all the way till the bottom. And what you have here now is going to be the values of probability for this distribution. So there, we have generated the probability values for the z-scores, and now let's plot it out and let's see how does it look like. So to plot it out, again, use the same concept, insert, go to recommended charts, and let's use this as an option. And there we have the chart ready, available to us. All right, so now that we have this chart, some very important things, very important concepts to look at. Let's just move it above, out here. Okay, here we go, almost there. All right, perfect. So in this one, if you take a look, what are the key differences from the previous normal distribution chart that we looked at? Now remember that instead of the mean of 60 that you just looked at, let's just stretch it a bit. Okay, so if you remember that in the previous normal distribution curve that we had plotted, the central point was the mean of 60. Here you will see the central point is 0 because every normal distribution has the central point as 0. And then you will see again that instead of the other values of x's, everything is replaced by z-scores on the x-axis. So instead of 90, if you remember, 90 was the last point that we plotted here and 30 was the first point. Here everything is in terms of standard deviation. So instead of 30 you have -3, and instead of 90 you have +3. So that is the advantage of a standard normal distribution. It will always have a mean of 0, and all distances will be measured as per standard deviations, and the standard deviation of this will be taken as 1 for this curve and for this distribution. So what is the advantage of this? The advantage of this is that when we want to compare two different normal distributions, and we have another one here, if we were to do the same thing for this distribution as well, then you will now be able to compare them on similar scales. So let's see how would that kind of work out or function. So let's just put these scores here, and then we will need the z-score and the probability as well. So how do we generate the z-score? Remember, the z-score is nothing but how far is the point from the mean. The mean for this distribution is 70, and the standard deviation for this is 5. So that will give us the z-score right there. And then all that we have to do out here is fetch out the formula. It's already there. And now once we have the formula, let's generate the probability for this using the norm distribution function. So we have the norm distribution function right here. The x is now replaced by the z-score, so we'll use that. What is our mean? Remember that the mean is 70. However, since we are playing with z-scores, the corresponding z-score is 0 for this standard normal distribution. What is a standard deviation? Standard deviation for a normal standard distribution will always be 1. And in terms of cumulative, do we want a cumulative? No, we don't want a cumulative. We just want a probability distribution function here. So let's use the option of false, and there we have our numbers. Okay, so now let's drag it out all the way, and now let's plot the normal standard distribution for this. So the normal standard distribution for this is again going to be plotted the same way. On this one, let's just make sure that we have selected the complete data set for this. Here we are. And if you go to recommended charts on this, all right, we still don't have the correct chart. Let's take a look at it and understand what has transpired here. Our score is 55. Let's see, 70 and 5 is the mean. Let's make sure that's what we have used. We have used 70 and 5. And it goes from -3 all the way till +3. And let's look at normal distribution function. So we've used the score right here, which is instead of x, you're going to use the z-score. We also have to use the mean value. The mean value is 0, and that's why the formula was not correct. We made that correction. Okay, now we are all right. As you can see, for 70, the mean value is 0, and we have the correct probability distribution. Okay, now let's plot this out. And there we are. And this time, instead of plotting it right next to it, we would want to plot it right below the existing standard distribution that we already had, so that we can kind of compare them. All right, there we are. Now, as you can see here, that it's probably going to be better if you look at it like this, okay? Because you should be able to see both of them together. So now, if you look at both of these distributions, obviously, while both of them are bell curved, and this is the central point around which you have the highest probability. Let's give it a different color, in fact. Right, so what do we see? The first thing that you'll notice is that within these probability distributions that you have, while it kind of looks similar, because remember that we have now plotted it all the way from -3 to 3, the same thing is here. But the advantage that this will now offer is that if you were to look at any of the data points in both of these, you will be able to compare them in terms of standard deviations, means how far or how close those data points are. And this is something that we are going to look at when we look at two different number sets and see how do they compare to each other. But this is an important concept. Again, bear in mind that what we had done here was your standard distributions. So we could just write it out here. This was your standard, this was your normal distribution. Call it normal distribution 1, and this is your normal distribution 2. Okay. And what you have here now is the standard normal distribution for the same data set. Just call it standard normal distribution 1, and this one is a standard normal distribution 2. All right, so that's what this one means out here. So as a simple example, if you wanted to compare data points from these two distributions, how would that work? So for instance, let's say on the first distribution, the point that we were interested in, so let's take a look at this. Let's say the point that we were interested in on this one is going to be 44. Now for 44, as you can see, this is the probability. It is 0.0110921, and on this, if you were to look at another number called, let's say, 66, the probability is 0.05. So given this information, are you able to make any assessments on where these numbers are within their own data sets? Probably not, because these are random numbers within two different data sets which have a different beginning and a different end, right? So now let's look at the same numbers here. So let's say we have 44, and let's mark this one, say in red color, and we want to compare it with 66. Okay, now can we make a differentiation? As you will see, the probability basis the z-score for 44 is 0.11. Now what is the probability for 66? The probability for 66, as you will see here, is 0.28. Since both of these distributions have now been standardized such that both of them have a mean at 0 and both of them have a standard deviation of 1, by comparing both of these, what we can clearly see is that 0.28, which is 66 out here, is greater than 0.11, which is for 44. In other words, 66 is far more closer to the center of the distribution, which is 70 in this case, as compared to 44, which is farther away from the central point of 60. So now, by looking at the z-score and by looking at the probability, you will be able to determine how 44 and 66 compare to each other within each of their respective distributions. So we can say that 66 is closer to the center within its own distribution as compared to 44, which is farther away within its own distribution. So that is the advantage and the value that you can get by developing the standard normal distributions or plotting them instead of just doing the in terms of just doing the normal distribution. This standard one helps us much more. Now, what other applications are there? So very common application that you will see pretty frequently is calculating probability. And how is this helpful in probability? So the way this is helpful within probability is, if you look at the curve of a standard distribution, if you take any 2 points, within the standard distribution, the area that you have between those 2 points gives you the probability of any data point lying between those two, between that area of the curve. That might be a difficult concept at times to understand, but let's look at that with a certain example. So let's say we wanted to understand what is the probability of x lying between, let's say the number 75 and the number 40 in terms of the distribution scale. Okay, so how would that work? So the way it would work is, if we had let's take an example. Let's say this here is where we have 70. So this line out here represents 70. Okay, so let's mark it, and let's say similarly this line here represents 40. So if the question is, what is the probability that a number will fall between 70 is marked here and 40 is marked here? So the answer is nothing but the area of the curve, the area of this curve right here, that lies between these two lines, the line at 70 and the line at 40. So this is another area of interesting application of normal distributions and the use of z-scores, and we should just explore that a bit further now. So let's move to that example. So that example is, there are 100 students that took an exam. The mean score was 60 marks and the standard deviation was 10 marks. Assuming that the marks were a normal distribution, which is the central assumption here, what is the percentage of students who received scores between 50 to 80 marks? So how do we solve for this? So remember that to solve for this, the first thing that we would need to know is we need to know the corresponding z-scores. And how do we get the corresponding z-scores? First of all, we'll plot out this normal distribution just like we did in the previous example, following which we will look at the z-scores, and from the z-scores then we can calculate the next thing, which will be probability. So let's begin. So let's say the normal scores that we have here, the normal scores are in what range? The normal scores will be in the range of, what is the average or the mean here? The mean is 60. What is the lowest that you can have here? So the lowest point of the distribution will be your mean minus 3 standard deviations. Remember, we are still using the same concept. The concept being 68, 95, and 99.7. So 3 standard deviations to the left of the mean, you will have your lowest score. So that then makes it, again, 30. 30 will be your lowest score. What will be our highest score? Our highest score will be nothing but the mean plus 3 standard deviations, which will again be 90. So basically we need all the numbers from 30 to 90. So let's begin with that. Let's plot it out. So same method as we saw in the previous example. Let's just drag these numbers all the way till we reach, let's say, 90. So these are some extra numbers that we have. We can just remove these out here. And all right, I think we have the correct numbers out here. And so with these numbers, now what we will do is we'll first of all convert this to our z-scores. So let's go ahead and convert these to our z-scores. Our z-scores for this will be nothing but each of these numbers, the difference from the mean. Remember, the mean is 60, and then divided by the standard deviation, so that we can see how far each number is from the mean in terms of the standard deviations. So there we are. This is the expected minus 3. Remember, this is the farthest point towards the left. And then if we were to look at the same formula, copy it, 90 is the farthest point on the right, which here represents the plus 3 standard deviation. All right, so we have the z-scores out here. So now that we have the z-scores out here, now the question we are trying to answer is, assuming that the students were a normal distribution, what is the percentage of students who receive marks between 50 to 80 marks? All right, so let's see. Let's mark out the first point. So 50, as we can see, is -1 standard deviations away from the mean. So let's mark this. This is 1 point. And then the other point that we have was 80. Remember, the problem we are trying to solve is what is the percentage of students who would have received between 50 marks to 80 marks. So this is one end of the spectrum. The other end of the spectrum is 80 marks. And well, interestingly enough, 80 is 2 standard deviations away. So basically, these are the 2 points. So what is the z-score for 50? It is -1. And the z-score for 80 is 2. Now, to solve these kind of problems, what we generally use is a z-score table. So what is a z-score table? The z-score table is a published statistical table. It is freely available online at various websites. Using that table, what we can find out is the probability or the percentage of data points that lie to the left of that point, basically. So what do we mean by that? So let's go to the z-score table and look at that number. So out here we have the z-score table. Okay, so here's the z-score table. It is split into 2 sections. What you see on the left hand side is the positive z-score table. The positive z-score table represents all data points to the right of the mean. What do you have out here again on the right hand side is the negative z-score table. This z-score table represents all the data points towards the left of the mean. Having said that, remember our first interesting z-score was plus, or was it? Let's just make sure we have the correct one. So for 50, remember it was -1. And for 80, it was the z-score table, the z-score was 2. So we are interested in 2 z-score, -1 and 2. So let's take a look at it. So for -1, as you will see here, the score is 0.15866. So let's just look at this. So yeah. So for -1, that's our z-score, 0.15866. Let's write that down. So 0.15866, that's one z-score. And then you have another z-score here, which is 2. Let's see what is the z-score for 2. So the z-score for 2 will be there on the right, on the left hand table, and for 2 it is 0.97725. It's 0.97725. So let's make a note of that. Okay, so we have both of the probability numbers for each of these z-scores. Now, in order to get the percentage of students between these two, what we have to do is just subtract these two numbers. So let's subtract both of these. So for 80, the z-score of 2, this was the percentage. And for 50 marks, which has a z-score of -1, this is the percentage. So if we subtract both of them, we will get the percentage between both of those. So here we are, and then just convert it to percentage. So that tells us that roughly 82%, or to be more precise, 81.86% of the students would have got marks between 50 to 80. All right, also let's look at this a bit graphically so that we understand this. To look at this graphically, what we'll just do is, let's just plot this out. And to plot it out, we'll just move this number here so that we can generate the probability distribution numbers. And then we'll be able to also graphically understand what this truly means. So let's go here and plot the probability. So to again plot the probability, remember we're using the norm distribution function. In this, instead of x, you'll use the z-score. Remember, for a standardized normal case, which is what we'll use here, for that, remember the mean is always going to be 0. Standard deviation is always going to be 1. The cumulative will be false for a probability distribution function. We have it here. And there we are. Now we have these numbers. Now let's go ahead and plot it out. Let's go to recommended charts. and use this, and we have our probability graph here. Okay, so let's take it here. Okay, so now in terms of the probability graph that we are looking at, what does it really mean? So, and this is an important concept, so pay attention on this one. So remember, we are looking at 2 points. The first point is 50, which has a z-score of -1. Do we have a z-score of -1 here? We do. This is the z-score of -1. And the other point that we were looking at is a z-score of 2, because the range was from 50 to 80. The z-score for 80 marks is +2 standard deviations. And let's mark out the +2 standard deviation here on the graph. The +2 standard deviation on the graph is probably going to be this one right here. All right, so now I think we'll have a better grasp of it. So if you look at the question, and the question said, what is the percentage of students who could have gotten marks between 50 and 80? When converted to z-score, we can state the same question differently. What was the percentage of students who would get marks between a standard deviation of -1, which is for 50, and a standard deviation of +2, which is for 80? So in effect, all of this area that you see between -1 and +2 standard deviation, this entire area right here, which is, let's look at it. Let's say we use this. So basically this entire area right here that you see. Okay. All right, let's build this again. So let's mark out this area. Just make sure that we have solid line and we don't need a fill. There we are. So okay, so basically this entire area that we are boxing right here, this entire area that you see under the curve represents the percentage of students who would have, and the probability rather, instead of the percentage, that's the probability of the students getting marks between 50 marks and 80 marks. So that's what this visually means. And as you can see that this covers considerable portion of the curve. This covers considerable portion of the curve. And as a result, what you'll see here is that 81.86% of the students have, that's the probability of students scoring between 50 to 80 marks. All right, so now we have seen a visual depiction or a visual graphical depiction of how probability works. So let's quickly revise the important points here. So if you want to calculate what is the probability of something between two events, what you'll do is, first of all, convert those events or those scores in this example to their z-scores. Once you have the z-scores, you can look up the z-score table. Basis the z-score table, you can then get the percentages from this table, as we did here, and then when you do subtract the percentages, you are going to get the scores out here. That's what we have done here. So we subtracted the percentages for -1 standard deviation, which is 0.15866, which is going to be this brown colored line right here at the left hand edge, and the percentage for +2 standard deviation, which is 0.97725, which would again be nothing but the right hand edge. And this entire area that you see of the curve right here, this represents 81.86% of the data set. All right, so now that we have seen this, another interesting way that this could be used is comparing data points. I'm sure all of us have heard of the idiom, apples to oranges comparison. Well, you could technically compare apples and oranges using a normalized data set. This is an example of a kind of problem that you could essentially solve by looking at this. So as you can see in this question, what we're being asked to do is to compare apples and oranges. So if we have a set of apples and a set of oranges, and let's say if you randomly pick an apple and an orange, given in this question, it is said that the weight of the apple is say 170 grams and the weight of the orange is 120 grams. Given this, and also given certain other characteristics of the data set, so it says that the mean weight of the apples data set is 200 grams with a standard deviation of 20 grams, and it says that the mean weight of the oranges is 140 grams with a standard deviation of 10 grams respectively. And it says, so given that data or given that information, how do these two compare against each other, the apple and the orange? So this is exactly the kind of problem that you will be able to solve using the same method. The method will be fairly simple. You'll plot out the data points of a normal distribution for the apples, and then you'll calculate the z-score for the apple. Once you've calculated the z-score, you will be able to use the z-score table out here. The z-score table will give you the percentage out here, the probability out here. And then you'll develop a similar table for oranges, and that will again give you the percentage. Basis the percentage, you will be able to determine how far or how close the sample of the apple and the orange drawn from the respective bags, how far are they away from their mean scores of both of those data sets. So this is a fairly interesting and important application, and this is how you can use Excel to solve some of these problems. Hope this was a informative video, and again, feel free to revise some of the information that we looked at from a normal distribution standpoint in the previous video as well. So that's all for today. Thank you so much for watching.